everyone. So this is a talk that was previously recorded for the Math Undergrad Student Association at UC Berkeley. They have a very nice seminar for undergrads every week, every Monday, and so this talk is really intended for someone who's taken calculus and like an intro to proofwriting class. So they know you should know like what a set is, but you don't need to know anything too fancy. Yeah. So the topic of this talk is going to be about how we can do calculus without referring to limits and without using any real analysis to make things rigorous. Because when we learn calculus, we're not thinking about limits. We're thinking about like algebra with very small numbers. I mean, you walk into a physics class and they'll say things like, "Oh, this is dx times dx, and dx is small, so dx squared might as well be equal to 0," kind of that sort of thing. And yeah, and that's the sort of thing that they say. Or they'll say something like the integral over all of m of f of x dx is summing up a bunch of small numbers that are like f of x dx. Dx is really small. F of x is like normal size, so their product is really small. And we're summing up all these numbers. And we would like to make these heuristics rigorous because they're very useful for calculation. I mean, we're going to do some examples in a little bit, and this is going to be quite a bit easier than like sitting down and checking the epsilon delta definitions that correspond to these things. So it's a reasonable thing to want to do. But first we need to figure out what do we even mean by a really small number? And I guess the technical term with that would be an infinitesimal. So let's say we have some infinitesimal, call it epsilon. What properties does epsilon have? Well, instead of referring to epsilon directly, we're going to refer to the set of what are called hyperreal numbers. So these are real numbers, and then we stick an epsilon in. So we take the real numbers and we add some infinitesimals. And we're going to assert some properties that this thing needs to have, and it turns out that we're going to be able to use those properties to define such a thing. So first of all, every real number is also hyperreal. That's reasonable. And there should be, not only should there be real numbers, but there should be another number called epsilon, which is infinitesimal. Epsilon is positive, and yet for any real number, which is positive, epsilon is less than that real number. So if I draw like a number line, let's say I got the number line, here's 0, and then we got this epsilon sitting right here, and then any positive real numbers are above epsilon. So your favorite positive real number, let's say 1 over 10, 1000 factorial. That is still greater than epsilon. So this epsilon really needs to be smaller than every positive real number. And yet, in spite of the fact that no such real number exists, we want the real numbers and the hyperreal numbers to be as similar as they reasonably can. And we're going to make precise what we mean by that. Yeah, what do we mean by the real numbers and the hyperreal numbers are very similar? Well, to do that, we're going to need to talk about what is called an ordered field. So what this thing is, it's an algebraic structure. It consists of a set of elements, and you can do addition on them. You can multiply them. Two of those elements are going to be called 0 and 1, and there's a binary relation which we call less than. Which satisfies a bunch of properties. Addition and multiplication are associative. It doesn't matter where you put the parentheses. They're also commutative. It doesn't matter what order you do them in. And if you add 0 to something, then you get that thing back. And if you multiply something that's non-zero by 1, then you get that thing back. You can subtract things. For any a, there's a minus a, and a minus a is 0. You can also multiply things. You can take a inverse, and then a times a inverse is 1. Or you can divide things, rather. Multiplication distributes over addition. If a is less than b, b is less than c, then a is less than c. And exactly, order is trichotomous, so either a is less than b, b is less than a, or a is b. And it cannot be the case that multiple of those are true. If a is less than b, then a plus c is less than b plus c. If 0 is less than a and 0 is less than b, then 0 is less than a plus c. These are properties that the real numbers have, and so it seems reasonable the hyperreal numbers should have them as well. And so the hyperreals had better form an ordered field, and that should be part of this criterion that I mentioned, that they should be very similar. Okay? So another thing that they should have in common should be something called elementary equivalence. To state what an elementary equivalence is, I should first define what a first order sentence is. So this is a first order sentence is a sentence that only refers to elements of an ordered field. It only refers to these guys A, B, and C. It does not refer to sets of these numbers A, B, C. For example, all of these sentences are first order. They only refer to the elements of the ordered field and not sets of the elements. The term first order can be made into like the term nth order by saying a zeroth order sentence doesn't refer to anything. First order sentence refers to elements. Second order sentence refers to sets. A third order sentence refers to sets of sets. A fourth order sentence refers to sets of sets of sets, and so on. An example of a maybe more complicated first order sentence is the sentence, a quadratic equation has a solution if and only if its discriminant is non-negative. Why? Because that sentence formally means, if you expand out all the definitions, for every triple of numbers a, b, c, there is a real number x, or there's a number x such that ax squared plus bx plus c equals 0 if and only if b squared minus 4ac is greater than or equal to 0. This did not refer to any sets. It just referred to the numbers and the operations plus minus times divide 0, 1 order that we gave them, and the numbers 0 and 1, because you can just write 4 as 1 plus 1 plus 1 plus 1. And so this sentence is true for the real numbers. I mean, this is another way of stating the quadratic formula, basically. And it is false for the rational numbers, because, for example, x squared minus 2 equals 0 has a positive discriminant, and it does not have a solution in the rationals. On the other hand, the completeness axiom, which you learn about when you take real analysis, is not a first order sentence, because it says for every set of real numbers, if that set has an upper bound, then that set has a least upper bound. And you might try to state the completeness axiom in a different way, but it turns out that no matter how hard you try, you will not be able to turn the completeness axiom into a first order sentence. And this basically means that first order sentences are not enough to completely characterize the real numbers. You need second order sentences to do that. And that's going to be very useful, because what we're going to do is we're going to say that the hyperreals are going to be so similar that they have all the same first order sentences, but they're not going to satisfy the completeness axiom, so they are missing some second order sentences. Okay, so if K is an ordered field and phi is a first order sentence, we say K satisfies phi if phi is true in K. So for example, the real numbers satisfy this sentence right here. For every ABC, there is an x, blah, 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 blah. And the rational numbers do not satisfy that sentence. And we say that two ordered fields are elementarily equivalent if for every first order sentence, K satisfies phi if and only if F satisfies phi. And a real closed field is an ordered field which is elementarily equivalent to K, to R, the real numbers. So what we really want is that this hyperreal field should be elementarily equivalent to the real field. It should be a real closed field. That's what we mean when we say that real numbers and hyperreal numbers are very similar. They're both real closed. Ugh. And if you've taken a logic class, you might realize that this is not quite enough. What I really am saying is that the hyperreals are an elementary extension. If you haven't taken a logic class, do not worry about that. Very mysterious. And so we should go back and check at some point that this thing is actually well defined. I mean, is it possible? Like, it might be the case that the property of not having any infinitesimals, which is true in the reals, is first order, and then any real closed field does not have infinitesimals. And that would be a problem, because then this hyperreal field would be just complete nonsense. It would not exist. Luckily, that turns out to not be the case, and we will prove this later on. But first, let's just take it for granted that such a thing exists and try to use it to do some calculus. Another problem with the hyperreal field is that there might be real numbers, or there might be hyperreal numbers rather, that are bigger than every natural number. The Archimedean property is second order. And in fact, if you start with epsilon, so epsilon is less than 1 over n for any n. For all n, epsilon is less than 1 over n. So that means that for all n, 1 over epsilon is greater than n, because the property, this property of like division, or like taking reciprocals, flipping the order, is a first order property. And so it's going to be the case that for every natural number n, for every n in natural numbers, 1 plus epsilon is greater than n. And so that can be expressed as meaning that while epsilon was infinitesimal, it was smaller than every positive real number. 1 plus epsilon is going to be infinite. It's going to be bigger than every real number. It's going to be way off in Narnia. And that's going to be weird. We don't want to run into trouble with those. So what we do is we say that if we look at a hyperreal number, we want to restrict the hyperreal numbers such that its absolute value is at most some natural number. Any real number certainly has this property. Just take like the ceiling of that real number's absolute value. Like negative 6.2 satisfies, if x is negative 6.2, we can take n to be equal to 7. And so we're going to let the standard part of x, denoted bracket x, just be x, but we set all the infinitesimals equal to 0. We map down from the hyperreals down into the real numbers, where there's none of this spooky infinite shit going on. So for example, the standard part of 1 plus 2 epsilon plus epsilon squared is just 1. This epsilon gets mapped to 0. Epsilon squared also gets mapped to 0. We just kill all the infinitesimals. Okay, so that being said, we can now define the derivative of a function on the hyperreals. Its derivative is the standard part. F prime of x is the standard part of the f of x plus epsilon minus f of x all over epsilon. A nice exercise in real analysis would be to check that this definition agrees with the usual definition of a derivative if f is just a function of real numbers rather than hyperreal numbers. All right, so let's work out the definition, the derivative of f of x with x to the n. It's going to actually turn out to be very easy. So f of x equals x to the n. F prime of x is the standard part of standard part of x plus epsilon to the n minus x to the n all over epsilon. Okay, now what is x plus epsilon to the n? That is x to the n. Well, the binomial formula is a first order sentence, so it is still true for the hyperreal numbers. And this property of like first order sentences are still true in the hyperreal numbers is called the transfer principle, actually. So the next term is going to be n epsilon to the n epsilon x to the n minus 1 plus, what is it? What's the second binomial coefficient? N times n minus 1. Oh, epsilon squared x to the n minus 2. And if you told me that there was going to be a pandemic that made it really hard to write on whiteboards, I would not have believed you a few years ago. But here we are. Bunch of extra junk terms, and then epsilon to the n. All right, so what happens to this? Well, this x to the n is going to cancel with this x to the n. And so this epsilon is going to cancel with this guy, so we're going to get the standard part of nx to the n minus 1 plus n minus 1 epsilon to the x to the n minus 2 plus some other stuff plus epsilon to the n minus 1. And we're taking the standard part of this, so this is just going to all, this all dies, and what's left is nx to the n minus 1. And that's what the derivative of x to the n is. It's nx to the n minus 1. So that was not actually very hard. Like normally you would have to like sit down and for every epsilon you have to pick a delta such that blah 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 blah. But here it was just like we wrote down the binomial formula and everything just sort of fell out very nicely. And that's just kind of how it is with these infinitesimals. And so this was our definition of the derivative. We also say that a function is continuous if for every hyperreal number, if you add epsilon and then you subtract off f of x, that just perturbs f by an infinitesimal. All right, and the classic theorem of calculus says that a differentiable function is continuous. So let's prove it. 1200. So a function being differentiable means that this thing, this standard part of f of x plus epsilon over f of x minus epsilon, this exists. This thing has a standard part. What does it mean for something to have a standard part? It means that there is some n. There exists n, a natural number, such that f of x plus epsilon minus f of x over epsilon is less than or equal to n. In other words, well, epsilon is positive, so f of x plus epsilon minus f of x, and this n we can just take to be like the ceiling of the absolute value of the derivative. That is at most n epsilon. And epsilon is infinitesimal. N is just a natural number, so n epsilon is still infinitesimal. That's a pretty straightforward exercise to check. So that means that this whole thing, well, this is an absolute value. It's at least 0. This whole thing is either 0 or it's an infinitesimal. And either way, that means its standard part is 0. The standard part of f of x plus epsilon minus f of x is 0. That is what it means to be continuous. So that wasn't so bad. Again, like we take out the usual like epsilon delta limiting argument and we just sort of write down the formula and we just take the standard part. Now, the reason why we don't just do this in introductory analysis classes is because the sort of construction of the hyperreals turns out to be kind of tricky. And it also turns out to be kind of ineffective in the sense that we're throwing around these infinitesimals and it's hard, like these things are infinitesimally small. It's hard to like have a computer reason with them. And so it's hard to use these for any sort of like constructive like reasoning. But maybe that's okay. In cases where you're not going to get any effective bounds in the first place, that isn't so bad. It's fine to lose some constructivity in that case. But again, the other problem is that these hyperreals are a little hard to prove that they exist. But that's what we're going to do. All right, so at the end of the talk, if you want and we have some time, we can try to do a calculus problem with infinitesimals. Well, and I guess I should say, because this is the recording on YouTube rather than the actual talk, that maybe you should try a calculus problem on your own with infinitesimals and see how you like it compared to doing it with the usual like real analysis approach. All right, so the theorem that we need to prove is that there is a real closed field, which we call R adjoint epsilon. It contains R, and when I say contains, I really mean elementary extension. Yes, sorry, nerds. Such that there is an element that we call epsilon, which is positive, and for every real number x is greater than epsilon, if x is positive. It turns out this is very closely related to an important problem that was studied by Henri Lebesgue at like around the 1890s, early 1900s, which is called the measure problem. What is the measure problem? It asks us to compute the length of an arbitrary subset of the real numbers. The real numbers form a line, and given some subset of the real numbers, we would like to know what its length is. And naively, what you would like to do is just take the function that is 1 on that set and 0 everywhere else and compute its Riemann integral. But if you've taken real analysis, you know there's lots of functions that don't have Riemann integrals. For example, the rational numbers do not. If you take the function which is 1 on the rational numbers and 0 everywhere else, that thing does not have a Riemann integral. And that's a pretty standard exercise in real analysis. For this reason, um, this measure problem turns out to be quite hard. Because we can't just use the Riemann integral here. We're going to have to come up with something a little better. So what we want is a function mu that takes sets of real numbers, subsets of the line. It takes subsets of the line and spits out either 0, a positive real number, or infinity, with the following property. If we have possibly infinitely many disjoint sets of real numbers, then their union should have length equal to the sum of the lengths. So this kind of makes sense. If I have, let's say this is a subset of the real numbers, and this is a subset of the real numbers. This guy is length 1, this guy is length 2. The total length of these guys should be 3. That is a very reasonable thing to demand. The second thing is translation invariance. If you take a set of real numbers and you shift it over, you're not really changing the length of it. You're just like changing your perspective, and that should not change its length. And the final thing is that the length of the unit interval should be 1 because it's the unit interval. These are all things that are very reasonable to demand of something that assigns length to subsets of the real numbers. Okay, and then Vitali came in 1905, I think, and proved that this is actually impossible. There does not exist a function mu with all three of these properties defined for every subset of the real numbers. And so we have to compromise. We have to restrict to special subsets of the real numbers where this thing is reasonable to define. So we call the set of all such measurable sets sigma. These are going to be the sets where the length is defined. And a measure on sigma is a function mu, which takes these sets, which are elements of sigma, and spits out a positive real number. And if you have disjoint sets x sub I, then the measure of their union should be the sum of their measures. And two useful properties that we can demand of these measures. One is that every finite set has measure 0. So this is basically saying that if you have a point all by itself, the point should not have any length. It should just be length 0. We say that mu is non-atomic if this is true, and otherwise we call that point an atom. Otherwise, another useful property is that every set should have measure either 0 or measure 1. This is very weird. This is nothing at all like length on the real numbers anymore. We're out of Kansas at this point. We are saying we're looking at measures such that everything either has length 1 or it has length 0, and there's no in between. That's very, very weird. There's nothing like length on the real numbers. Anyways, so Borel proved a little theorem which says that there is a sigma, which is called the Borel sigma algebra, which contains every useful set. I'm not going to make precise what that means. If you want, take a course in measure theory. You'll also prove Vitali's theorem while you're there. But it contains every useful set. And there is a measure mu defined on sigma, which is non-atomic, translation invariant, and it's calibrated. It is not Boolean valued, clearly. The interval of length 0 to a half has length a half. It does not have length either 0 or 1. So this measure mu that Borel came up with solves the measure problem sort of, because it gives you the length of every useful set. It just can't determine the length of like very complicated sets that have very bad properties. So this was like a compromise solution to the measure problem. It does not give you a measure which is Boolean valued. That's going to be very important later on, but certainly length on the real numbers is not Boolean valued. So an interesting thing, it would be say, let's find a set lambda such that every subset of lambda can be measured in a way which is non-atomic and Boolean valued. So finite sets will have measure 0. Finite subsets of lambda will have measure 0. And every set is either going to have measure 0 or measure 1. In particular, the complement of a finite set should have measure 1. This is very weird, again. But maybe we can look for a compromise, again, by saying maybe this condition that when we took like a sequence of sets, x sub I indexed by the natural numbers, that their union should commute with mu. Maybe that was too much. Maybe we want to just say if we have finitely many sets, let's say x1 through xk, we want we want x1 through xk. This is finitely many sets, and they're disjoint. We want the union of them to have measure equal to the sum of their measures. That's a bit weaker because we're not requiring that this is true for infinitely many sets x sub I, only k many, where k is some finite number. That seems like it might be possible. And that's exactly what we're going to do. There is, in fact, a finitely additive, non-atomic, Boolean valued measure defined for every subset of the natural numbers. So we can just take lambda to be equal to the natural numbers here. How do we prove that? Well, let's see. So for every finite set, it has to have measure 0. So let's just say mu of that set is 0. And then mu of the complement of that set is 1. So this will mean that the set is non-atomic. The measure is non-atomic, sorry. And so far it's Boolean valued. Everything either is measure 0 or measure 1. And so let's just choose any set x that we haven't assigned a measure to yet, and just say, okay, this set we just arbitrarily chose it to have measure 0. Now there are a bunch of criteria here: finitely additive, non-atomic, Boolean valued. And so in the act of setting that set to have measure 0, we inadvertently force a bunch of other sets to have various measures. For example, the complement of x now has measure 1. The union of x with any finite set now has measure 0. The union of x with any set which had measure 1 now has measure 1, and so on. So by assigning a mu of x equals 0, we assign a bunch of other sets measures as well. Now, there's still like sets that we have not assigned a measure to, but we can just repeat this process forever. And if you've taken a logic class or an algebra class before, you might recognize this is Zorn's lemma. We are using Zorn's lemma here. If you don't know what Zorn's lemma is, cool, that's not terribly important. The point is that this theorem is true. We can assign, by making a bunch of arbitrary choices, we can assign a measure which is only finitely additive, non-atomic, and Boolean valued to the natural numbers, or rather to sets of natural numbers. Great. So this is the technical tool that we needed in order to prove that hyperreals exist. Notice that for the real numbers, we did not need anything nearly this fancy. If you've taken a real analysis course, you've proven that the real numbers exist, and you use like Dedekind cuts or Cauchy sequences or something much that did not require any of this fancy Zorn's lemma crap. Let me just move my... Can I move my display? Yeah, there we go. My display over to the corner. Okay, so let's say we have an ordered field K. Let k to the omega be the set of sequences in K. So these are like infinitely long lists of elements in K. So these are just like numbers in this K, which had order, it had multiplication, it had addition, it had 0 and 1. And we're looking at sequences in K, and we have a finitely additive, non-atomic, Boolean valued measure on the natural numbers. By the way, such a thing is usually called an ultrafilter on the natural numbers. So mu is our ultrafilter on the natural numbers. And if we have two sequences, x and y, we're going to say that x is similar to y if and only if the measure of the set of natural numbers, such that x of n equals y to the n, x of n equals y sub n is 1. Example, if x and y agree on all but finitely many entries, then their measure is 1. If they, then x and y are similar. So the similarity is an equivalence relation. And we can let pi of x denote the equivalence class of x. That's just like, we're saying if two sequences are similar, after applying pi, we now consider them to be the same. So if two things agree except on a finite set, or on one of those arbitrarily chosen sets that when we use Zorn's lemma, we're saying, these sequences are similar enough, we might as well think of them as the same. And to denote that we're thinking of them as the same, we write pi of x for the equivalence class. Okay? So we then do something kind of bold, which is we say, let's just say pi of x plus pi of y equals pi of x plus y. And so you can do similar things for multiplication, order 0 and 1. And you might worry that this thing right here, pi of x plus pi of y equals pi of x plus y, depends on the choice of representative that we're using here. We start with pi of x and pi of y, and then we take x and y from them. And it turns out it doesn't matter how you like go backwards from pi of x to x. This is an exercise in algebra that I will not prove just because it's kind of technical and annoying, but it's not very difficult. It has to do with the fact that this thing is finitely additive. Okay, so that means we have relations addition, multiplication, order 0 and 1 defined on the set of equivalence classes. And you can check, oh, let's go all the way back. We had this thing, this definition of an ordered field. You can sit down and check all of these different relations that an ordered field has to satisfy, and you will conclude that in fact, our friend that we just constructed, this thing that we call an ultrapower, the set of equivalence classes equipped with addition, multiplication, order 0 and 1, is an ordered field. When we call it the ultrapower of k with respect to mu. All right, so let's just choose some mu arbitrarily. There's lots of them. Pick some ultrafilter mu. And let's just say r of epsilon is the ultrapower of r with respect to mu. And we should check that this thing is a hyperreal field. But at the very least, it's a real, or we haven't even checked that yet. Okay, let's say we know that it's an ordered field. We need to check that it's a hyperreal field, and before that we need to check it's real closed. Okay, well, we're going to use something called Walsh's theorem. Walsh's theorem says if k is an ordered field and f is its ultrapower, then k and f are elementarily equivalent. Now, what does it mean to be elementarily equivalent to r? It means you're a real closed field. And that was part of our definition of a hyperreal field, was that it was real closed. So Walsh's theorem says that r adjoint epsilon, which we just said, oh, it's just some ultrapower, we don't really care which one. R adjoint epsilon is a real closed field. And if you've taken a course in logic, then Walsh's theorem is not very hard to prove. You just induct on formula complexity. The only hard part is that when you want to do the existential inductive case, you need to use the axiom of choice, because you have to pick an equivalence representative. You have to go backwards from pi of x to x, and that's the axiom of choice. If you haven't taken a logic class, those words were just complete gibberish, and that's fine, because you do not need to know what those words mean in order to understand the rest of the talk. That's good. Okay. So if x is a real number, we want to assign it to some hyperreal number, and in fact, we assign it to the hyperreal number pi of the sequence x, 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 just on for infinity. And so that is injective. You can check. This is an injective function from the real numbers to the hyperreal numbers, so it's reasonable to think of the real numbers as a subset of the hyperreal numbers. As for this epsilon, this infinitesimal, we take the equivalence class of the sequence 1, 1/2, 1/3, 1/4, and so on. And for any positive real number, x, after finitely many entries, x is greater than 1 over n. So the measure of the set where x is greater than 1 over n is 1. Sorry, this should be x is greater than 1 over n. So epsilon is less than x. And by a similar token, epsilon is greater than 0, because 1 over n is always greater than 0. So this thing, epsilon, is going to be smaller than every real number, which is positive, but it's going to be greater than 0. So it's an infinitesimal. Okay, and we're done. We did it. We showed that a hyperreal field exists. I mean, you have to check Walsh's theorem, and you have to check all these technical details, which is why we do not do this in an introductory real analysis course, but it wasn't so bad. Hyperreals exist. Great. And I see that I have like 10, 15 minutes left over. So let's just, before we go back and do some fun calculus problems, if this was an actual talk and not just me talking into YouTube, let's just do something for fun. I earlier asked if we could find a set lambda. And when I say set, I'm going to think of two sets as equal if they have the same cardinality. So I'm just going to call these things cardinals, which are like equivalence classes of sets. So find a cardinal lambda such that there is a non-atomic Boolean valued measure on 2 to the lambda. And we said this is really hard. We had to like weaken our assumption from measure to finitely additive measure. And then we were able to do this when lambda was the natural numbers. But, let's just go nuts and try to come up with an example when lambda is a lambda is a cardinal. Okay, so if there's a non-atomic Boolean valued measure, not finitely additive measure, but actually countably additive, if there's a non-atomic Boolean valued measure on 2 to the lambda, we call lambda a measurable cardinal. Okay, so here we're going to do something brave and say, well, what if measurable cardinals exist? Okay, so to understand the properties of measurable cardinals, I need to introduce this technical device called the Grothendieck universe. So what is a Grothendieck universe? It is a set with the following properties. The natural numbers, not like each individual natural numbers, but the set of natural numbers is in U. If x is in U and y is in x, then y is in U. We call such a thing a transitive set. If x and y are elements of U, then the unordered pair x comma y is also in U. If x is in U, then the set of all subsets of x is also in U. If f is a subset of U, the elements of f are all sets, and there is a bijection from f to some element of x, so f isn't too big, basically, then the union of f is also in U. So these things are huge. They're closed under every operation, basically. Because this thing contains the set of natural numbers. By this property, you can show it follows that it contains all the individual natural numbers. You can use this property to show that it contains the real numbers and the hyperreal numbers and any other algebraic structure you want to come up with and all of their elements. It contains, I don't know, whatever your favorite mathematical object is sitting inside this thing U. Assuming U exists. Assuming U exists, every set you've ever cared about is inside U, even if U is the smallest one possible. And by an inaccessible cardinal, we mean the cardinality of a Grothendieck universe. Okay, so a theorem, which I'm not going to prove because it's a bit technical, but it really describes what these measurables are like, is that if lambda is a measurable cardinal, then lambda is inaccessible. So lambda is the size of a universe, but on top of that, the set of inaccessibles under lambda has cardinality lambda. So like, not only is lambda a universe, it is not only is lambda the size of a universe, it is the size of a universe that is made out of universes. It's like a multiverse kind of. So why are these things so big? What is wrong with them? Well, let's let V denote the class of all sets. I'm not going to say the set of all sets by Russell's paradox, but we can sort of talk about the class of all sets if we're careful and we know what we're doing. V is the class of all sets. Lambda is a measurable cardinal, and that means there is a non-atomic Boolean valued measure mu on 2 to the lambda. Let's let V to the lambda be the set of all functions from lambda to V. Now, a sequence is a function from the natural numbers into V, but this is a little bit bigger. V to the lambda is a set of all functions from lambda into V. And let's again talk about the usual equivalence relation where a set x is similar to a function x is similar to a function y if and only if the set of elements of lambda on which they agree had measure 1. So they agree on most of lambda. And then we let M be the class of equivalence classes, a class of similarity classes in V to the lambda. And this thing we can, these guys, V and M, aren't really ordered fields, but they're kind of like ordered fields. The technical term for them is an LST model, but never mind that. And so M is an ultrapower of V. So we took the entire mathematical universe, the class of all the sets, all of them, and we made it bigger by throwing in a bunch of junk, in the same way that we turn the real numbers into hyperreal numbers by adding infinitesimals. Okay, that's a little weird, but let's just put our doubts aside for the time being and say let's let J be the inclusion map from V into M. Previously, we had a map. I didn't call it J, but that's what it is. J sent the real numbers into hyperreal numbers by saying X just maps to X, basically. And that's exactly what J is going to do here. It sends a set to itself in the bigger universe. Oh boy. This thing is going to be really big. Okay. Let lambda be a measurable cardinal. And M is an ultrapower of v with respect to lambda. Then v and m are elementarily equivalent. And if x is smaller than lambda, then j just sends x to itself. But if j of lambda makes lambda bigger. Okay, so like under lambda, nothing changes when you apply j. But if you apply j to lambda, you get a bunch of extra junk inside of lambda. And so what this means is that measurable cardinals must be very, very weird because they can just perturb the entire mathematical universe. This is just crazy talk. This is just baloney. And so if you know a little bit of logic, it should not come as a surprise to you that we cannot prove that Grothendieck universes exist, and we cannot prove that measurable cardinals exist. But it is highly unlikely that the opposite is true. We shouldn't be able to prove that they can't exist. So I think a lot of set theorists would just tell you that measurable cardinals exist, and leave it at that. But yeah, we were first talking about very small numbers, infinitesimals, and we were like, let's just go nuts and see what happens if we try to weaken, or if we try to strengthen our definition of an ultrafilter, and we got these really big numbers as well. So yeah. Oh, and if you know some set theory, you should try to use measurable cardinals to prove some theorems. Prove that the consistency of 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 blah 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 of the consistency of ZFC is true, and prove that there exists a set which is not constructible. If you don't know what those words mean, cool, because not a big deal. Okay, and so where did I learn these things? Well, the measure theory I learned from Pugh's book, Real Mathematical Analysis, chapter 6. It's very good, and for a more advanced treatment of it, more advanced than we need here, Lang's Real and Functional Analysis is also very good. Coincidentally, chapter 6. Model theory, I learned it from a book by Ted Slayman and Hugh Wooden, and edited by two UC Berkeley students, actually, Jaffa Volano and Matt Park, called Introduction to Logic, the UC Berkeley course. This is where you can learn about things like first order sentences and Walsh's theorem and so on. Ultrapowers and infinitesimals I learned from Terence Tao's blog, where he uses them. He has two posts: ultrafilters, non-standard analysis, and epsilon management, and minimal dynamical systems recurrence in the stone check compactification, where he uses ultrapowers and infinitesimals to prove some. He talks about how to use them to prove some pretty heavy-duty theorems in analysis. In modern analysis, there are often very complicated technical arguments in that it's like for every epsilon there is a delta, such that for every n there is an eta, such that for every k there is a kappa, such that for every rho there is a... And it's just a nightmare where you have to worry about epsilon, which is small, and eta, which is very small, and kappa, which is like very, very small, and n, which is very large, and it's just a mess. And infinitesimals can simplify arguments a lot. A very powerful tool. So this is not just like, oh, let's just have some fun and prove some theorems from calculus. This is actually a very powerful tool in modern analysis. And then Evan Chen wrote up some lecture notes from some lectures by Peter Kollner about set theory and large cardinals that are on his website. And I can send you links to any of these books or these blogs if you would like to learn more. So yeah. And I guess before we take questions, we have a few minutes. So if anyone has a calculus problem that you want to try to do with infinitesimals, maybe we can do it.